I was working on this calculus problem of a sliding ladder. Here I have a little animation of it right there. And it was a calculus problem, and they said the top of the thing moved down at a constant velocity, and then they wanted to find something about the horizontal velocity. And I was thinking, I don't know that that's the way it would really do it, right? It wouldn't move down at a constant velocity. So let's do this as a physics problem. And in fact, I found a physics problem like this, and it said, suppose you have a frictionless ladder. We're doing frictionless. You can add friction, but it gets a little bit more complicated. And the question is, at what angle does this lose contact with the wall? Because if the ladder's sliding and it's falling over like that, it's going to eventually lose contact with the wall. Let's do this problem. There's a lot going on here, and I'm actually going to do it 3 different ways. Kind of. Okay, so let's get started. Here is our ladder problem. So I have a ladder leaning up against the wall. Center of mass is at the center of the ladder. So I have a length L, the length of the ladder, and it's at some angle theta, and that's going to change. I'm measuring theta from there. I've seen other people do it different ways, but that's where I'm going to do it. Now, I really want to look at the center of mass motion for this ladder. So that ladder is going to have a center of mass position, a y position, and an x position. So we have the location of the center mass. I'm assuming this is the origin right there. Okay, so let's model this thing, this ladder. So I have a stick, right? I have a stick. I have the center mass of the stick. And I want to think about what forces are acting on this stick. I have the gravitational force pulling down. That's pretty easy. It acts at the center of mass, assuming a uniform ladder. And then I have a interaction with the wall, and that's it's a normal force, so it's perpendicular to it, and it pushes in the x direction, and then a force pushes in the y direction. So I have these 3 forces acting on it. Now, and then we can use that to apply Newton's second law. Newton's second law says the net force on the center of mass tells me how the center of mass moves, right? That's what Newton's second law tells us. It tells us something about the motion of the center mass. It's also going to rotate. Okay, so if it rotates, I have to also include the net torque about some point. I'll use the center, since we're using the center of mass. It's going to be the moment of inertia times the angular acceleration. And that's how we would do the problem, you would think. But this is a tough problem. What makes this so difficult? What makes this so difficult is that we actually don't have an expression for this force. We don't have an expression for that force. They're contact forces. They're forces of constraint. We don't have equations. We can say that force is going to be whatever it needs to do to keep that end of the ladder on the wall, right? And the N2 is going to do whatever it needs to do to keep the bottom of the ladder on the floor. But we don't know those. Okay, so let's think about this in a different way. I'm going to set up the equations for you first, though, because they are kind of useful. Here I have the ladder. They're the same forces acting on it. We do need some point about which to calculate the torques, and so that would be right there. And then I need these angles. So that's my angle theta, but I want the angle of N2 with respect to this torque arm right here, which would be theta. For N1, this angle is theta. So I can do the net force. That's pretty easy. The net force in the x direction is just N1. So that's mass times acceleration in the x direction. The net force in the y direction, I have 2, right? I have N2 and I have gravity pulling down, and that's mass times acceleration in the y direction. And then I have the torque, right? So I have the torque due to N1. This is going to be in the negative z direction. I wrote it as a scalar because of the right-hand rule. And this would be the torque arm, L over 2, and then I want the component of this force perpendicular to that torque arm, which would be N1 sine theta. So there's negative because it's rotating that way, and then N1 sine theta is the perpendicular force, and L over 2 is the thing. And now the torque for the N2 would just be positive, right? Use the right-hand rule, L over 2 again. But this one uses cosine. You see that? Cosine theta. And then the gravitational force doesn't exert a torque because it's at the center of mass. And this would be I times alpha. And again, I'm writing this as a scalar value. When we have problems like this, we have problems with constraint forces. We could do something like Lagrangian mechanics, and that would work really well. But I just didn't want to do that. I want to approach this from a standpoint of someone in introductory physics could possibly do it. You could possibly do it if you know work energy and rotational motion. You could do this problem. So let's not use Lagrangian. And we want to find out when that ladder loses contact. So instead, let's use the work energy principle. So here's my ladder, and I have these angles. I'm measuring the angle of the ladder with respect to theta right there, x and y. And I'm going to look at how things change because I want to find velocities. So the first thing I'm going to do is to use notation. And this does come from classical mechanics, so don't freak out. But I'm going to, instead of writing dx dt, that's my x velocity, I'm going to write that as x dot. It's very, very common in classical mechanics to use this dot notation. It looks cool, and it's easy, and it makes things more compact. So x dot is the derivative of x with respect to t. What about the derivative of y with respect to t, you might say? And yes, it's y dot. And then we have another one that we need to think about, and that's the derivative of theta with respect to t, because the angle's moving too. This would be the angular velocity theta dot. Okay. Now, if I have the work energy principle, I want to think about what's my system. So my system's going to be the ladder plus the Earth, and that means that I can have gravitational potential energy. So the gravitational potential energy, if I call y is equal to 0 on the floor, it'd just be the mg times the height of the center of mass y. And that would just be L over 2 is the center of mass times sine theta, right? So the height of this, the y value is L over 2 sine theta. Now, when we think about the system of the Earth and the ladder, we want to think about what forces are doing work. And so we have the gravitational force. It's acting on it, but it's part of the system, so there's no work done by gravity. And then we have those two normal forces, but they don't actually move, right? The displacement for those forces is 0, so no work done. Okay, so there's no work done in the system, and that's what's nice about picking the Earth plus the ladder. Now, for the kinetic energy, I actually have two types of kinetic energy. This ladder can have motion. It can move in the x and y direction, and it can also rotate. So it's going to have translational kinetic energy plus rotational kinetic energy. For the translational kinetic energy, it's just 1/2 mv squared. But if I think about that in 2 dimensions, that's I forgot the mass. I'll put it back in later. You know there should be a mass there. It's 1/2 m times x dot squared plus y dot squared, right? Because x dot squared plus y dot squared is the velocity. Because we have the x velocity squared, the y velocity squared, we get the total velocity squared. And then we have the rotational kinetic energy. It'd be 1/2 I omega squared. That's how we do rotational kinetic energy. I is the moment of inertia, right? A property that depends on how that mass is distributed about the axis of rotation. Scalar version of moment of inertia. We're not doing inertia tensors. Nope. 1/2 I, and I'm going to write omega as theta. So I have 1/2 theta dot squared. So those are my two kinetic energies. So here is my ladder, there's my x. So my translational kinetic energy, again, I left off, I just copied it. And then my x, so I need to find x dot, I need to find y dot. So x, oh, that's wrong. I had it fixed in another picture. Weird. Okay, so x is from here to the center of mass. So x is L over 2 cosine theta. The picture's wrong. And now I can take the derivative of x with respect to time. So that's going to be equal to negative, I have to take the derivative of cosine. So the derivative of cosine theta is negative sine theta, but the chain rule still applies. So I have to take the derivative of the inside of that. I have to take the derivative of theta with respect to t. So I get this theta dot right there. That's what that is. I'm going to need x dot squared, so I just need to square this. L squared over 4, I move the theta dot over here. Theta dot squared sine squared theta. Now let's do it for y. Y is L over 2 sine theta, take the derivative, y dot is cosine theta, theta dot, square that, y dot squared, there's a dot right there, is L squared over 4, theta dot squared, cosine squared theta, and now I can add those together, and I did put the m in this time. So when I add these together, I can factor, when I add x dot squared and y dot squared, they both have this L squared over 4 theta dot squared. I can factor that out. So I have 1/2 from the kinetic energy, and then 1/4 from that term. So I get 1/8 m L squared. I can factor out the theta dot squared, and then I have sine squared theta plus cosine squared theta, which is equal to 1. So I get that for my translational kinetic energy. Boom. Okay, my picture's wrong here too. So this is the wrong picture. There's my x and my y, which are wrong, but that's fine. You'll be okay. And there's my rotational kinetic energy. And so I can just write that as I theta dot squared. I haven't determined what I is. I'll put that in later. And then I have my translational kinetic energy. I have my gravitational potential energy, which also depends on theta. So everything depends on theta and theta dot. You see, I'm getting in a theta equation. Now my initial energy, what we're going to do is start with the ladder almost vertical. It's not going to be quite vertical or we'd never fall over. So my initial energy, right, if the work is 0, then the energy is constant. Change in energy is 0. So if I have my initial energy, I can set that to equal to any energy later. So my initial energy, it's not moving. It's just gravitational potential energy, mg L/2. And then my energy at some other time later would be my translational kinetic energy plus my rotational kinetic energy plus my gravitational potential energy. And so this is an equation that has theta and theta dot in it. And that's really what we want to look at. And I'm going to solve this for theta dot, okay, for a number of reasons. So to do that, it's not too hard, right? I can just move these. I can factor out the theta dot squared out of that and then do some, that's all I did right there. That factored out the theta dot squared, and then I moved this term over here. So if I subtract mg L/2 from both sides, I can factor out the, what happened? Oh, the 2, I multiplied everything by 2, so that's gone, that's 4, gone. And then I subtracted that. So I get mgl 1 minus sine theta. And then this stuff over here is just going to be ml squared over 4 plus I. That's an I. And then I factored out the theta dot. Now I can just divide both sides by this to get theta dot squared, mgl 1 minus sine theta, and then have that ml squared over 4 plus I. That's not a 1, that's I. And then take the square root of both sides, boom. Now I have to point out something. You know, the way my ladder moves, I'm actually measuring theta in the wrong direction. It will all be fine in the end, but it was just a from me. But this is pretty important. That tells me how theta moves, right? And right away you can see that theta is not constant, right? Because theta dot's not constant. Theta dot depends on theta. So as theta changes, theta dot changes. So right, going back to the calc problem, that this is not going to move at a constant velocity. Okay, so now let's think about what would happen. How do we find out when the ladder loses contact? So here's my ladder, and there's that normal force with the wall, right? And that normal force is going to make this accelerate that direction. So it's going to increase in speed that way. Until at some point, the way we have it, I said the x, it has to stay there, right? It has to stay on the wall. So as that ladder starts moving away, eventually the wall is going to pull it back the way I have the math done. And that this normal force would change directions. But if it's a real wall, then it wouldn't do that. So really what we want to do is to find out when this normal force is 0 or when the x velocity is, the change in the x velocity is 0. All right, because it's going to be moving that way. It's never going to get pulled back. But it's going to be will if it's attached to the wall. It's going to be moving away from the wall, and once it stops accelerating away from the wall, that's when it loses contact. Okay, so let's do this. Here's my ladder. One of the things, I have this ladder. If you have a ladder that's like a rod, then it has a length m and a length L and a mass m, then its moment of inertia will be 1/12 ml squared. And if you want to know how to find that, it's really not too hard. I have a video on that. I'd be happy to redo it, but that's what that is. Now, for a reason that will be apparent later, I don't want to use this. I don't want to use a ladder like that. Instead, I'm going to use a ladder like this. My ladder has the mass broken into 2 pieces, m/2 and m/2, separated at the ends, and then the stuff connecting between them is massless. So I can calculate the moment of inertia for this. It's going to be the moment of inertia of this piece with respect to the center mass, which is mr squared. So the m is m/2, r is L/2, so you square that. And then I have that one over here too that has the same thing. And when I add those together, I get L squared over 4 m over 2, but then I get 2 of them, so that 2 cancels, and I just get m over 4L squared. And that's my moment of inertia that I'm going to use. And the only reason I'm doing that, just to make things look a little bit nicer, right? We want to make things look nice. So here's my theta dot with my moment of inertia I. And if I just put in my value for my moment of inertia, mL squared over 4, it looks like that. And this looks a little bit nicer, right? I can get things to cancel. All the masses cancel. The L doesn't quite cancel because I have an L on the top and an L squared on the bottom. So I get this, and then I have 1/4 plus 1/4. So that's just going to be equal to, I can bring that as 1/2, and then I bring the 2 up top, and I get that. So 2g 1 minus sine theta over L square root. So that should have units of radians per second. So this sine theta has no units, 1 has no units. G is in meters per second squared, and I divide by meters, I get 1 over second squared. I take the square root, I get 1 over seconds, which is radians per second. So that's good. Okay. I feel like I made my equations too small. Oh well. I'm not changing it now. What do you think I'm doing? Going back? I'm 16 minutes in. You're 16 minutes in. I can't throw that away. Okay, so we want to find an expression for the horizontal acceleration because we want to find out when the horizontal acceleration goes to 0, from it's going from positive to negative, that's when the ladder loses contact with the wall. Here's my expression for x. Here's my expression for x dot. We had that already. What about x double dot? X double dot would be the second derivative of x with respect to time. So I just need to take the derivative of this with respect to time. And you'll notice I actually have a product here. I have a theta dot and I have a sine theta. So I take the derivative of sine theta, I get cosine theta, but then I have to take the derivative of the thing inside. Don't forget that. That was my problem I always made a mistake of. So I get another theta dot. That's theta dot times theta dot is theta squared. And then I take this negative L over 2 sine theta, I have to take the derivative of theta dot, and I get theta double dot. So that's my acceleration in the x direction. And remember, I want to set that equal to 0. So I have 0, and that's just the same thing. And the L's cancel, the 2's cancel, and I can write this as, move this to the other side, cosine theta, theta dot, equals negative sine theta, theta double dot. That's what we want to solve. We want to solve this for when this is, what value of theta makes this true. And it looks tough, right? Because we have a theta dot in there, we have a theta double dot in there. So that's fine, because I have an expression for theta dot. I can put this in there, it depends on theta. I can put that in right there, right? I can put in theta dot squared, right? Because that's really what I have. I have this. I can just take the square of this and put that in. That's what I'm going to put in right there. But what about theta double dot? Well, I'm going to have to take this and take the derivative. So here's my theta dot. I'm going to write it as, I'm going to get all this 2gl and put it as a constant. And then I have 1 minus sine theta to the 1/2 power. That, nobody wants to think of square roots, right? You always think of it in terms of power rule. So I can write that whole thing to the 1/2 power. Now I can take the derivative of that. And so the 1/2 comes down in front. That's right there. And then I reduce that by a power of 1/2. And then don't stop, right? You got to take the derivative of the inside stuff too. And that's going to be the derivative of negative sine theta is negative cosine theta. You got to take the derivative of that inside too. And you get theta dot. So that's my theta double dot. So I'm going to put in this for theta dot squared. I'm going to put in this for theta double dot squared. Theta double dot, not squared. And then we can see what happens. So here's that equation. There's my theta double dot, simplified just a little bit. Notice right here that I have a 2 and a 2. So if I bring this in to the square root, it'll be 1 over 4. So I'll have 2 over 4. So I end up, really what this does is bring 2 into the bottom. Okay. And so putting that in for theta double dot, this equation becomes this. I just put this right there. The only thing difference is that I have the 2 on the bottom right there. Now, you'll notice that I have a theta dot and a theta dot squared. So this theta dot cancels with that squared. So I don't have a theta dot over here, and I only have 1 over there. And then this was my expression for theta dot. If I put in this for theta dot, I get this. And I know it looks like, oh my gosh, it's too fast. I agree, it's too fast. This is a lot of trig, but it's not hard, or algebra. It's just algebra. All I do is put in this for that, right? So then I have cosine, cosine. This thing is that. Negative sign is negative sign. And then this is that, but the theta dot's gone. Okay, so we have some canceling here. The first thing is, if I multiply both sides by the square root of 1 minus sine theta, I have a square root of 1 minus sine theta over here. So that's just going to be the square root, the square of the square root. So I just get 1 minus sine theta. That's kind of nice. Next, you'll notice that I have this g square root of g over L on both sides. Canceled. Okay, and then I have these 2's, right? I have a square root of 2 on the top here and on the bottom here. So when I multiply both sides by the square root of 2, I just get 2. So with that, I get this. Cosine theta, that's that right there. This is my, now I have the square root went away because I multiplied it by this. And then the 2, oh, I didn't do that yet. And then I have the square root of 2 over there. And then this is negative cosine theta. So that's all fine and dandy. Okay, so here's where we're at. Move to another page just for space. Same thing. Those cosines cancel. And these square root of 2's turn into a 2. So I get 2 times 1 minus sine theta equals sine theta. I can solve that, right? That's not too hard. Multiply out the 2. 2 minus 2 sine theta equals sine theta. I'm going to add this to both sides. I get 2 equals 3 sine theta. And then I just take the divide both sides by 3. And then I can take the inverse sine, and I get theta equals 41.8 degrees. I did it. And that's the angle that the ladder loses contact. And I'm measuring that from the floor, okay, not from the top wall. Now, I said, theoretically, I said it shouldn't depend on I. That angle should be the same, okay? Now, one way to do that is just to say I is some constant times ml squared, and then you can see that you still get the same thing. I didn't do that, so I'm just assuming that. I saw that, but if you want to check that out, that's fine. But what we did was we just found the angle that it lost contact. But what about the whole motion? How do we find the whole motion of the thing? Let's do that. And we're going to use a numerical calculation, and this is the Euler method. So here's my, this is a differential equation, right? I know the theta dot as a function of theta. So if I can use my, some steps to model this in time, then I can get the whole motion. So what I'm going to do is to break my motion of the ladder into short time intervals, delta t. And you can pick how small that is. But if delta t is small enough, then during that time interval, I can assume that this is constant. So I can calculate the value of theta dot and assume it's constant during that time interval. If theta dot's constant, I can write it like this: delta theta over delta t. All right, the theta dot is the derivative of theta with respect to t, but if it's constant, it's just a difference, delta theta over delta t. And then if theta 1 is my angle at the beginning of the time interval, theta 2 is at the end, then I can write that as theta 2 minus theta 1. I can solve that for theta 2, and I get that. Theta 2 is theta 1 plus delta theta delta t. Theta dot delta t. And so what I do is I just calculate theta dot. I use that to find the new theta, and then I just keep doing that forever. And you do need to start with an initial value, right? Because if I want to find the new value of theta, I have to have the first value. So let's just pick 1 degree. It doesn't really matter. And it got cut off by my giant head right here, and I apologize. But degree, there's 2 e's right there. It's right there behind my head. Here's how we do that in Python. And I will give you the link to the code down below for this full program. I'm using WebVPython. I like to use WebVPython because there's no magical modules that just say solve or anything like that. We have to do everything by ourselves, and it also is pretty good with the graphing. So this is it's in a web browser. So that's what this WebVPython 3.2 does. It's not really important. Line 2 is making a graph. I'm going to make a graph of theta versus time. And then that's just part of the function I'm going to plot. So you don't really need to know about that. Here's my initial angle, theta. I'm using radians, right? So if I want 1 degree, I have to convert that to radians, pi over 180. And then here's my initial angle, which I don't need. I calculate that. Whatever, it's there anyway. And then I don't need g. I do need I do need g, right? Because I have theta dot has g and l. So I need g and an l and t and dt. I put 0.01 seconds. And this is just running for 1 second. Calculate theta dot. That's that equation. That's just that equation in Python. That's it. And then I use that to update theta, right? And remember, in Python, this is the make equal to sign. So you don't have to say theta 1, theta 2. I just change the value. And then I plot it, and then there's time. And this is the angle as a function of time. That's it. It should be it should be getting smaller. What did I do wrong? It should be negative. Yeah, it should be negative. So it should be. I have the angle from theta. What did I do wrong? Because theta started at 1. Oh, that's why. I did do that backwards. I should have theta starting at 90 or pi over 2. Okay, that's fine. What about the velocity, right? Because that doesn't give us the answer. So here's my velocity. It depends on sine theta and theta dot. And here is, all I did was to add in, I made another plot, and I calculate the x velocity based on that equation right there. And then I took off the negative sign again because I made it in the backwards. I think I made a mistake here, but it works out in the end. And then I plot it, and when I do that, I get this. This is the velocity. The x velocity is a function of time. And the velocity increases up to some point right here, and then it decreases, and you'll notice that point up here where the velocity, the acceleration, the slope of that line is 0, is 41. So it works. Okay, let's do another method, right? If you can do it one way, you can do it 2 ways, and you can do it 3 ways. So here's another way to do it. And I'm going to have my 2 masses right there, my 2 mass ladder, and that's why I picked that. And I'm going to say that everything is a spring. So the ladder is connected, connecting these 2 masses, that's a spring. It's a spring. So I know that if I move one end of the ladder, it's going to move the other end of the ladder because they're connected by a spring. The wall is a spring. So if this mass pushes into the wall pushes back. And that's one way to deal with these forces of constraint, is to treat them as though they're springs. And the floor is a spring. Okay? So everything's a spring. So I can calculate the net force on this, gravity, plus the interaction with the wall, plus the interaction with this, and the same thing for this one down here. Once I do that, I calculate the force, the net force on that, the net force on that, and then I can use that to update the momentum using the momentum principle, and then I can update the position. Should work, right? Okay, so it's a little bit longer program, but it's fun. Here's the first part, the setup. I have the length. I made the floor and the wall are just boxes, right, so that you can see them. The spring constant, I just picked a value. The mass of each ball, I just picked something again. Try changing these and see how much of a difference it makes. My initial angle, and this one I know I did right. I measured the angle from the top for this one. I'm not sure why. Okay. So then I just make mass 1, it's a sphere. Mass 2 is a sphere. The spring connecting them, I just call it it's a cylinder. G, I'm using a vector G. Okay. And then the initial momentums of both the balls and the time step. You're going to need a smaller time step. And here's all the magic. So I ran it for 3.2 seconds because I played around with it, so just like it when it leaves. And I'm not sure why the time seems long. Oh, no, I do know why the time's longer. Okay. So this rate 1000, this tells Web v Python to not do more than 1,000 loops per second, and that makes it run in real time. This LR is a vector from one ball to the other for that spring force. Because if one gets pushed in, I need to know what the distance and the vector location between them so I can calculate the spring force pushing them apart. This is the spring force on ball 1, right? So there's a spring constant. I have the magnitude of LR minus L, which is the unstretched length of the two balls. And then this norm LR is a unit vector in the direction of LR. So I get this as a vector force. Vectors are important. You can't just say, oh, I'm going to calculate the spring force and be done with it. It has to be a vector. So then at the beginning of each loop, I calculate the force. I assign it that m1.f is the net force on that ball. And it's gravity plus the spring force. Now, mass 2 is minus the spring force, right? Because there's two balls. If ball 2 pushes on 1, 1 pushes on 2 in the other direction. Line 28 right here just says, okay, is that ball mass 1 pushing into the wall? So I set the wall to x equals 0. So if it has a negative x value, x position, then there's a spring force. And that's what this does. This calculates that spring force based on that. Now remember, I want the x position only. So m1.pos.x is just the x value of that vector position. But then I need to multiply it by a unit vector in the positive direction, 1, 0, 0, to make it back into a vector. If I didn't do that, I can't add it to this. I can't update the forces. I can't by adding a vector and scalar. You can't do that. And then I do the same thing for mass 2. This line 32 updates the momentum of mass 1, update the momentum of mass 2, update the position of mass 1, update the position of mass 2, update the position of the spring connecting them because you want it to look cool, update the axis, and then I did calculate theta, and so that I can plot position as a function of theta. Okay. What does it look like? Here we go. Is it moving? There it goes. Now, if you have your time step too, you can actually, or your spring value too low, you can actually see the ball shaking and stuff, which is kind of cool. But it seems to work. If you let it run too long, this just stays on the x equals 0. So it kind of just, no, it doesn't. This stays on the y-axis though, because it can't go below that. This can go in the positive x direction, so it just kind of moves away and swings around, which is not like a ladder. But if you plot the x position of this mass as a function of theta, it looks like this. So we actually start over here. We're shaking back and forth, right? We're shaking because we're pushing up against the wall. And these are really small values, 10 to the negative or 0.01. 0.01, so 1 centimeter. So I should probably make spring constant greater. And then over here, as it starts shaking around, eventually it loses contact with the wall and just gets further and further away. And I got 38.8 degrees, which is not 41, but it's kind of close. So you can see that it's, because it's not perfect, but it's kind of cool, and I'm really happy with the way that worked out. So I have two programs there. I have that first one, a numerical calculation, which I know has an error. I'll probably fix it before I post it. And then I have this one, which is the animation, which I think this is really just fun, right? I like doing this way. Everything's a spring. It's fun to do. Whew. Okay, so you see, it started off as a simple calculus problem that I didn't agree with, and I made it an awesome physics problem.